Hello, Pre-Calc. This is your only notes for our little mini lesson on matrices, where we will define matrices and their components, add, subtract, multiply matrices by a scalar, multiply two matrices, and the main reason we're doing this is learn about determinants, because you will need them in the chapter on vectors. So this is our little mini unit. So let's start off with what is a matrix. So it is basically shorthand. It is a way of organizing your numbers without all the variables, or in a more exact, it's a rectangular array of numbers. So to notice, we have rows. So this would be a row, and you have columns, and we define the size or the dimension of a matrix by the rows by the columns. So a 2 by 3 matrix has 2 rows and 3 columns. So this first one has 2 rows but 3 columns. 3 by 2 matrix, 3 rows, 2 columns, etc. Okay? So it's always rows, then columns. If the matrix has the same number of rows as it does columns, we call it a square matrix. So say a 2 by 2, 3 by 3, etc. Each number in a matrix is called an element, and it has a specific position. So for instance, in this first matrix up here, this -1, that would be row 2, column 1 is how we would refer to its position. Row 2, column 1. That element is -1. So then, we had that. Okay. And two matrices are equal if and only if they have exactly the same elements. So meaning they look exactly the same numbers. Then we have this idea of the diagonal. So you have the main diagonals where you start in the upper left corner, and my controls over here are a little bit in the way, so I'm going to move this over a little for a second. So this would be the main diagonal. Now, the diagonal is really important when you're using matrices to solve systems of equations, which we are not going to have time to do this year, but that's one reason why we'd want to know about the diagonal. And a diagonal matrix, so you have a main diagonal in a matrix, but if you actually have a diagonal matrix, it is a square matrix. In other words, again, that means like 3 by 3, 4 by 4, same number of rows, the same number of columns, with zeros everywhere except along the diagonal. And again, that's really important when you are solving systems of equations, which is not going to be our main goal this year. Okay, working with matrices is actually pretty easy when you're adding, subtracting, and just multiplying by a scalar, because all you have to do is find the corresponding elements. So for instance, and I'll write out the specifics, if I'm adding these two matrices, so this is a 2 by 3, and I'm adding it to a 2 by 3. In order to add two matrices or subtract two matrices, they have to have exactly the same dimensions. So you have to have the same elements positioned alike. So for instance, to add them, I basically add the elements. So 5 plus 4, 2 plus 6, 7 plus 8, 1 plus 5, 3 plus 1, 9 plus 3. So like first element in each, I'm adding together. And then we just simplify. So we have 9, 6, 8, 4, 15, and 12. If you're subtracting, basically the same idea. So we have a 2 by 2, we're subtracting a 2 by 2, they have the same dimension. Whoops, sorry, shadow, I just kicked my cat. So you'd have 6 minus 4, 5 minus 7, 2 minus 5, and 3 minus 2. So you can see it's really pretty straightforward. This would be -3 and 1. So adding and subtracting, nothing really outstandingly difficult there. Multiplying by a scalar, also not very difficult. You just distribute the scalar to everybody, everyone. It's kind of like a dilation factor, so everyone gets dilated by the same amount. In the end, this becomes 10, 15, 20, 30, 5, and 35. And that would be multiplying by a scalar. If you are solving an equation using matrices, we can, so again, this is a 2 by 2 equal to a 2 by 2. So if I want to solve for x, I just set the same elements, the like elements, equal to each other. And I can then solve, so I have 5x equals 10, which gives me x equals 2. If I want to solve for y, I set the y elements equal to each other. So that was row 1, column 2, y minus 4 equals a -8. So we have that y is going to equal, I'm going to add 4, that's still a -4. And for the z, I set the z's equal to each other. 4z plus 6 equals 2. So you get 4z, that equals a -4. Z equals a -1. So you can see matrices are pretty basic. Basically, if I had a system of equations, each row would represent, say, the coefficients in that system. But you can see adding, subtracting, multiplying, not too bad. Multiplying two matrices is actually a little more involved. It's not quite as easy as adding and subtracting. But one of the nice things is when we get to vectors, which is right after this unit, this will be equivalent to finding the dot product of two vectors. And we'll talk about the significance of that when we do the vectors, but it's nice you'll have this introduction. So the way you multiply two vectors, first of all, in order to do it, they have to have the same inner dimension, not total dimension. So for instance, a 2 by 3 can multiply against a 3 by 4 because the inner dimension here, 3 and 3, matches up. The result is the outer dimension, which would be a 2 by 4. The reason why they have to match up is because when you are multiplying, you're multiplying a row by a column. You multiply the elements, but you add the result of those multiplications. So, in other words, A1 goes against X1, here would be the result, gets added to B1 times X2. And that would be what goes in row 1, column 1. To get to, say, this result down here, we took row 2 and multiplied it against column 2. So this is row 2, column 2, where A2 got multiplied against Y1. The second element got multiplied against that second element in the column, and then you add the result. All right, so let's go ahead and try one of these. So we have here DE, which is a 2 by 2. E is a 2 by 3. Since the inner dimensions match up, we know the result is going to be a 2 by 3. So we'll work it out. We're going to do row 1 against column 1. So that's going to be 7 times 3 plus 0 times 5. Sorry, I don't know if you can hear my cat meowing at me. We had a stressful day at the vet today. So then row 1, column 2 is going to go in row 1, column 2 position. so plus 0 times 4. Then I'm going to have row 1 times column 3 goes in the row 1 times column 3 position, 7 times 6, plus 0 times a negative 2. All right, we are done with row 1, so I'm going to erase that, and we're going to move on now to row 2. So with row 2, we start with row 2 against column 1. It's actually hard to talk about it than just do it. This gets added to 3 times 5. And then we have row 2 with column 2. So that's going to be 5 times a negative 3 plus 3 times 4. And lastly, we have row 2 with column 3. So that's 5 times 6 plus 3 times a negative 2. And then we put it all together by simplifying it. So 21, and then we have a negative 21, and then we have 42, and then we have, what, 15 plus 15, and negative 15 plus 12, and then we have 30 minus 6, which is 24. And that would be the result for that vector. Okay. I'm going to just double check my work here. Dun, dun, dun. Okay, that looks good. All right, so if I had to find ED, notice that E, again, is a 2 by 3. D is a 2 by 2. The inner dimensions do not match up, so we would say not possible. And if you had to justify why, you would say inner dimensions don't match. Inner dimensions don't match. All right, then we have this very special product that we're going to do. I know this looks ugly, but it's not. This is a 2 by 2 against a 2 by 2, so I know the result will be a 2 by 2. And so we're going to first do row 1 with column 1. That's going to give me 3/5. Negative times a negative is a positive, so I'm going to add to that 2/5. Then we're going to do row 1 with column 2, which gives me 3/10 minus 3/10. Then we move on to row 2 times column 1. That's going to be 4/5 minus 2, oh, yes, 2 times a negative 2 is a negative 4/5. And lastly, trying to see what color I haven't used yet, row 2 against column 2 is going to be 4/10 plus 6/10. And the big ta-da, when we simplify this, you get 3 plus 2 is 5, 5/5 is 1, 3/10 minus 3/10, 4/5 minus 4/5, and this is 10 over 10. That was kind of a little wonky. Let me move that over. All right, this, when you have ones along the diagonal and zeros off, is called the identity matrix. And the identity matrix is really special. It's always a square matrix, meaning same rows, same number of rows, the same number of columns. If you multiply anything by the identity matrix, it's like multiplying by 1. You get back what you started with. And it has some really special properties in matrices if we were going to get deeper into it, but we're not, because what we really care about right here is we care about the determinants. Okay, so let's talk determinants. Dun, dun, dun. So determinants, it is a number. That's the first thing. It is just a real number, one number associated with that matrix. It has a lot of applications. You can find the area of triangles, determining if points are collinear. You can, oh my goodness, solve equations using something called Cramer's rule. There's all kinds of things you can do with determinants. And we will be looking at one of the applications when we go into vectors. We're going to just focus on the sort of the rote process of finding the determinant in a matrix. Now, a determinant of a 2 by 2, super easy. But first let's talk notation. So determinant, we tend to say the determinant of A. Notice this A has straight brackets as opposed to the square or sort of, staple looking brackets of a matrix. So when you have these straight absolute value looking lines, it actually is saying find the determinant. How do you find the determinant? It's basically cross multiplying A times D minus B times C, and that's it. That would give me the number that is associated with that matrix as a determinant. Okay, so to find the determinant of matrix B here, I have negative 3 times 2 minus 1 times 5, so I would have a negative 6 minus 5, which is a negative 11. So a 2 by 2 matrix, really friendly. And they're nice. They're really, there's something called Kramer's rule. If we have time, it'd be really awesome to show you. We used to teach it in Algebra 1. It is a really nice way of solving a quick 2 by 2 system of equations using matrices, but we'll see. What we really care about are the determinants of a 3 by 3 matrix, and that's because when we look at vectors, we'll be looking at vectors in 3 dimensions, so that means we're going to need the 3 variables. All right, so we have to do a little bit of a back talk before we get into this. These are called third order determinants, not something you necessarily have to really know. And the way you do it is an expansion of a minor. And you're like, what's a minor? Okay, so if I choose an element, so I choose this first element, row 1, column 1. After I choose that element, I cross out the row it's in, and I cross out the column that it's in, and notice I'm left with this 2 by 2. That is called the minor of that element A. If I was finding the element of row 1, column 2, this element B, I would cross out this row, cross out this column, and notice DF, this is the minor that is associated with B. Also then notice I move down the row a little further to E, I cross out that row, I cross out that column, and you get the minor that is associated. Notice it has the absolute value brackets. So to find that determinant, again, you just do the whole cross multiplying routine. There is one little caveat to that. So in order to expand, and again, when you do expand, you can expand on any row. This one we just did row 1. But I can expand on any row or any column I want. And in general, what you want to look for is zeros, because they make it really easy, because multiplying by 0, sorry, I just keep kicking my cat, she's by my feet. Okay, so underneath, invisible to the naked eye, is this sign pattern. This is super duper important. Let me give it a big exclamation point. It's super important because this sign chart, and it keeps expanding. If you had a 4 by 4, 5 by 5, you just keep, alternating the pattern, starting with a positive in that row 1, column 1 position. That sign pattern underlies each element in the matrix. So when I'm finding a determinant, up here, notice the minor was A, that had a positive in front of it. The second one, that has a B, that B element has a negative sitting behind it. Now, how does that affect what we're going to do? When you expand, let's say we're going to again go, we're going to do column 1, I guess it looks like. if I wanted to expand and find the determinant of this 3 by 3, I start with this first, so this is a plus. I always like to kind of write it so I don't forget about it. So remember, we take that first element, here it is. That means you cross out the row, cross out the column, and it gives you the minor, which is a determinant. Then when I go to the second element, it's minus because it has a minus underneath it. That second element, so with that one again, we're now going to cross out the row and the column. So notice you have B1, C1, B3, C3, and we would find that determinant by doing the cross multiplying. And then we go on and we get to the third element, A3, which has a plus behind it. So we're going to cross out, whoops, hey, why is my eraser not working? Okay, my eraser doesn't seem to want to work. That's fine. Okay, here we go. So I cross out. Okay, now let me use my pen, you silly people. So cross out my row, cross out my column, and notice now I have B1, C1, B2, C3, and we would find that determinant. Okay, that was probably totally confusing, but let's do it. We are going to expand across the second row. So here is the second row. There is a minus, a plus, and a minus sitting behind those numbers. So what I would do, I'm going to start with the -4, and that's going to get multiplied by the matrix that results from when I cross out its row and its column. So this is -1, 3, 8, -3. All right. Now we move on to the next element in that row, which is 0. I'm going to write it out, even though once you get a 0 in front of thing, obviously 0 times anything is 0, but just so you see the pattern, okay? So what we want to do is cross out its row and column. Sorry, I said that backwards, column and row. And I'm left with 0, 3, to -3, and then we come to the last element, so let me get rid of this, in that row, which is now a -3. So if you didn't have that signs below, you would have said +3. So it's really important you know that the signs alternate behind those elements. So when I cross out its row and its column, I've got 0, -1, 2, 8. So now I'm ready to just find my determinant. So this is -4 times -1 times a -3 minus 3 times 8. Then we have plus 0, and I'm going to work it out even though I know it's going to be 0. So this is going to be 0 minus 6, and then lastly we have -3 times, this will be a 0 minus a -2, and then we bring it all together. So -4 times a -21 plus 0 minus 6. So what is this? 84 minus 6, and the computer keeps turning off on me. Sorry about that. So the final drum roll, please, is we get a determinant of 78. And you're like, oh, that was exciting. So again, we're just going over sort of the rote, how you would find a determinant, and we'll talk about its application and meaning when we get into vectors and we're actually working with it. Okay, but you can see vectors are really kind of fun. We want you to know how to do them without a calculator rather than just hit a button and have the calculator do everything for you, which I think is important. Some colleges are taking the calculator away from people's hands, and so we will come back to this towards the end of our unit on vectors, but for now you just have a worksheet to work on.